Hello, my name is Bertrand Nouvel. I'm one of the member of the WideIO, which is a company that does valorization of algorithms that is specialized also in video analysis. I have two other members of the companies that are here today, Jonathan and Bernard, and we will be splitting the talk in 3 parts. It's an introduction to action recognition in Python. So we will review. It's quite an ambitious program to do in 1 hour and 20 minutes because, well, action recognition, you have to go to understand how to read a video, how you're going to get the meaningful features, understand what these features means, and let's discuss also why it's interesting to do this in Python. To start this talk, I will give you an overview of what we want to achieve during this tutorial. It's an interactive tutorial. You're welcome to ask questions if there's anything it's not a lecture. It's something that we have to. It's a tutorial, so I expect you to don't hesitate to if you have any question about what we're doing. After, as I said, there would be a first part that will be related to video processing. How do we open a video in Python? How would you see it? How do we link that with NumPy? There is a second part that go inside of the machine learning details and inside the video processing details of the pipeline that we will be implementing to recognize actions. And then we'll put all that together and make it work. So the first step is, of course, for you to have an environment ready. I know that you have been all asked to install either an account on your computer, either to have a Wakari account. We really expect that you have this. You have to know that we will be using OpenCV2, and OpenCV2 is not available on all Anaconda platforms. It's only available on Linux platform. Otherwise, you may have to install OpenCV2 yourself or to connect to Wakari to do the part of the tutorial that require OpenCV2. You have the URL of the repository that contains the source code, so I really invite you to copy it and to download the content of this tutorial. Meanwhile, I will be doing the blurb and explaining a bit more about who we are. As I mentioned, we are a startup right now, and we help academics to democratize the best algorithm. So what we do is that we allow people that have innovative ideas to put their ideas on the cloud so that they can be accessed by people that need them and that don't have the knowledge to implement such techniques, and that require basically to be connected with academics to solve the problems that they have. And we're specialized in image analysis. We also run a consultancy where we try to solve the problem that our customers have in image analysis. And we recently released an application for Valentine's Day that was detecting kisses, people kissing and giving them voucher. And basically, the talks that you have today will be giving you some elements that we use behind this application. Also, I'm sure you all, if you're here, you all know about Python, and you're sure that Python is great. But I think when we do a talk that's about computer vision and Python, actually lots of people in image processing and computer vision, they come from MATLAB. And it's probably a good thing to remind why actually it's a good idea to do computer vision in Python, or let's say MATLAB, but it could be C and C++ and Fortran. And there was initially this idea that to be the best, we need to get the best performances. And the only way to get that was to use difficult language like assembly language directly and not to do anything with high-level languages. And I think what happens now with Python is demonstrating the opposite, having a language that's multi-paradigm, in which you can write in the way that you like, where you have reflections, where you can actually analyze how the code is written so that you can rewrite it in another language, where you have operator overloading so that you can use a normal plus in between two matrices and not call a specific function, having a large community and having some things that's used by administrator in the web and in sciences is actually a great benefit for all of us. It's also a language that's quite lightweight. The bytecode and the Python interpreter is quite light compared to many other environments, and we have a great community, and in the end, the code is very readable, and we have something that's fast to code and to run. I hope you are already with the download of the data, or you're probably still processing this. I know there's a few megabytes, so I'll continue to start to explain now what is the pipeline we're going to implement. So what is action recognition? So it's a classification task where the data sets that we have are composed of videos, and where we want to label these videos according to something that's semantic. We want to say, okay, there was an object in that video that did this. And historically, I would say one of the first data sets that was used was human action data sets by Ivan Laptev. And it's a quite simple data set today, but it still has a reference. And you had to classify 8 actions, like running, jumping, saying hi, and well, so what we're trying to do is to make some meaning out of these images. And obviously, as it's something that's very interesting, making meaning out of data, there are lots of people that wanted to do it, and for a while. So it's, as I said, it's an ambitious topic to want to talk about action recognition and to do an introduction on that. So we can't cover everything. There are systems that recognize one type of action, like the one we've implemented, and because it's one type of action, you can actually do include lots of prior in the algorithm if you want to boost a little bit the performance, if you're able to do so. These systems, because you're talking about video, when you talk about video, actually you're talking often about multimedia. So you're talking about accessing not only the images, but also the sound that is related to that images. So you have, if you have the sound, you may use a continuous speech recognition, which is another topic of research. But you have basically people that try to extract the meaning with a more holistic approach, trying to combine features that come from the sound and from the images. You have the, I would say, fairly traditional pipeline, that the one we would be discussing about, which are basically on which we cut some specific features, and we use standard machine learning after, and we use information that are apparent in terms of local features inside of the image to classify the videos. And you have approaches where actually you say, actually, I don't even want to learn the features, like deep learning, and you have even less priors. So as I said, we will be focusing on a very traditional pipeline, and it could be this pipeline. We could see it everywhere in natural language processing, in audio segmentation. You find it very often. It's very classic. You have your data. You know your data because their rows are not in the right format. You inject some knowledge by specifying where are the features, how you're going to reduce the amount of information that you have, and then once you have data that is carrying enough information in your opinion, you apply machine learning, because then traditional machine learning techniques have a chance to work. In our case, the data, as I said, are video frames. We're going to make them sparser, as I said, and we're going to use a classification method, and more exactly, bag-of-keypoints in terms of feature, and support vector machines for the machine learning. That is the moment where we may want to start to have access to the code. Is there still someone that doesn't have access to the code? Seems all right. So as I said, the first part is about video processing in Python. Video processing implies to read videos and to presently write videos. And in the open source world, the reference library is called FFmpeg. Unfortunately, the wrapper for FFmpeg hasn't been maintained for 3 years, and I know that because I was a maintainer of this package until 2010. I couldn't maintain it after and couldn't find any new maintainers. For a few people suggested they would continue it. It hasn't been continued. FFmpeg has evolved, so you can't use that lightweight wrapper anymore, but you have a wrapper that's available through OpenCV. So if you do computer vision, you're likely to want to use OpenCV, but it's not a very good wrapper if you want to process video because you can't really seek accurately in the images. It's sufficient for scientists that know that they have simple data and want to go one image after the other. But if you need to seek in the video, if you need to extract sound, you probably would prefer MLT, which is the MediaLovinToolkit, which is a great package that's not very known and that has been developed by broadcasters in order to do many operations with their videos. And it's also the backend of many open source video editing software. So it's quite powerful, and I really invite you to have a look at it. In our cases, we are with Anaconda and Wakari. Obviously, OpenCV is only included in Anaconda on Linux and not on Mac and Windows, and MLT is not part of Wakari, of Anaconda yet. So the solution for today would be to have to access a small video file. So I invite you to go into the part1 folder, and you have a small script called get-akio.py. If you run that file, it will just download a sequence of JPEG files that will be readable by PIL and will allow you to work today using a sequence of images. Obviously, I invite you to use the other libraries normally if you process videos, and I've included inside of the source code a folder called VIO. It's not VIO, it's VIO now for video IO to avoid any conflict. And you have different players, and you can see basically how you can open a file and with MLT, with OpenCV, and get the frame one by one. After you have the documentation of each website if you want to go further, but at least you have 2 players of videos that you can use to start to do video processing. And you have a third one called PIL. For displaying images, we have kind of the same problem. Of course, we have Matplotlib that's there, but Matplotlib is designed for creating figures. It's not designed for rendering videos that are 30 frames per second. And OpenCV has some primitive too, but as I said, it's not necessarily available. And I recommend that you actually use a library called Piglet, which is an OpenGL, a small library for developing OpenGL applications. It installs quite easily. It requires to have OpenGL on your platform to work correctly. And it works on all platforms, maybe not Windows 64, for I tested that recently. It was working on Windows 32 very well, but maybe there is. Otherwise, you can use Qt directly. Same thing, inside of the VIO folder, you have an element called displays, and they are objects, and they all have the same interface, and they allow you to display images one by one. You can run these ones, and if you run display Qt.py after having downloaded the video, you should be able to see the video of Akio. So I can do that here. So as you can see, I'm using Anaconda, and I'm inside of this folder. I use Python pass equal dot because I don't know the way I did the module was I did that quickly, and it might be necessary to do that. It depends on your environment. And if I run that, you just see the video being displayed as fast as possible. So there's no timer on it, but you've seen the sequence of images being displayed as fast as possible. So you should be able to run that I would say all of you, if you have Qt installed, I mean, if you have Anaconda, which is normally the case, you should be able to access that. We continue on now and start to discuss about processing these images. And we'll go further into what we call key points and what are interesting key points. But I think if we do video classification, we want to, and action recognition, we want to find inside of the images what are the points that are interesting. And the points that are interesting in images are generally the corners. We can discuss about what is the right definition, but I would suggest that you start with a classical Harris corner detector that's composed of, as you can see, 3 elements in terms of mathematics. There is a smoothing that is applied to the image to remove the grittiness and not to have corners, but there's no corners. There is a gradient that will basically detect edges. And there is this formula that should remind you a little bit of a determinant, and basically is indeed a determinant in the tensor space, and actually allows you to select not the edges, but the intersection of the edges, which are the corners. If we want to do action recognition, it's not object recognition. It's maybe very similar in terms of framework, but to get action recognition, what's interesting is to link visual features with movements. And the way to do that is to compute the optical flow. And if you have a look at this file, the optical flow, we're not going to re-implement it in Python today. It would be too long. But it's available through OpenCV. And it's very simple to use. And you can make it accessible for an object, so you can switch from one implementation to the other nicely after if you want to. It should be key points and not key ponats. And you can have a look at this file called custom feature. If you have a look at this file, it's not finished. And the idea is that right now, actually, we've got a key point detector, so we can select in images points that are interesting. And we've got the optical flow of the image. And all this is provided you as code. But if you want, we can take maybe 2-3 minutes and for you to have a look at the code as this file called custom feature. And then I will open it in front of you, and then see if you want to complete the little bit of that are missing in Python about how we're going to do that feature. So as I said, here we're using the Harris corner detector we've just coded before. It was also available in OpenCV, but I thought it was interesting to see it. Then we've got optical flow, which is just calling the OpenCV version of it here. And then we're going to do some kind of key point extractor, which should detect the key point, okay, and basically compute some descriptors by using a local feature at the point where there are the key points. So I gave you a function that retrieves the patch of the image at this specific location. Might not be exactly the right shape if you're on the border. So if you look at the code, it says, OK, well, we create the optical flow once we get the first image. And then we process the optical flow. Obviously, the first time it will be the same image, assuming because we don't know what would be the movement, so we assume everything is frozen. And then we go for concatenate the intensity image of the color image with the flow, which is just a D stack in Python, so it shouldn't be too difficult. The images are the same shape, and that's easy. Then get the key point. It's just calling the previous Harris detector that we had before. And then go through the compute the local feature at each position. I will run that example in front of you. I will run it remotely because as I said, there's not OpenCV in Anaconda on Windows, nor on Mac, but I can run it from here. And no. So here what you see is that each frame, I I display the optical flow here that has been computed by optical flow in OpenCV in the window. And here you've got the position of the key points. I haven't displayed them. And here you've got the descriptor associated to each key point. In that case, I just took, if you look at the code, you have the solution. I mean, you have the compute feature normal, and the compute feature answer, compute feature solutions that give you an example of feature that is just basically what was the optical flow and the color at this point. Well, that's all for the introduction on video processing, the part 1 of the tutorial, and I will let Bernard explain you how you can implement better each step of the pipeline.
Okay. While I set up the computer, you can go to the folder called part 2 and start looking at the code. The first step is the feature extractor. Yeah, it's working. Yeah, okay, so the first step.
Sorry, where can we download the code?
If you are in Wakari, you can go to the console and execute the JIT sentence, this one, and you have the code.
If you're doing Wakari, you have to pull up a shell to do it.
Well, if you don't have the code, I can just explain it because I have the code here. I will explain its code, okay? So the first part is to extract the features, and we have two main steps. The first one is to detect the key points, because the image have a lot of pixels, but not all of them are interesting. And we have different algorithms for that. And we use the so-called space scale. So we have the image, we reduce the size of the image, and we apply different blurrings. So we have key points detected that are robust to scale variation. The second step is to describe the key points. But the key points, they are only one single pixel, so we need to define the region around the key point. In this case, we are explaining SIFT, but depending on the algorithm, they define different regions. So we compute the gradients, the magnitudes, and the orientation, and we put all of them in a vector. We call this descriptor vector. And depending on the algorithm, SIFT has 128 elements, while SURF has only 64. So we can go to the code. First, we import the libraries. CV2 is to extract the features. SciPy is only to get the Lena image. And then PyLab to plot, and NumPy helps us. So we define here, you can see them, the detector list and descriptor list, so we can compare them. We get the image here. And with OpenCV, it's really easy. We just have to call this instruction, feature create, and you create the detector, the descriptor. The first step is to detect the key points. And with those key points and the image, you can describe them with descriptor compute, and then plot the results. Here are the results, and you can compare them. Maybe you are thinking why the circles have different sizes, and this depends of the of the scale space. If the key point was detected in a scale space that was very small, so the image was very reduced, we have a bigger point because we are having more information about the area. And then the line that you can see here is the most important orientation of this region. So if you want, you can play with them, change the features, extractors, and detectors and descriptors, and you will see that, for example, fast is only a detector, but not a descriptor, while SIFT implements both phases. If you have the code, you can try to do this example. It's an exercise. The homography is just to filter the matches, because what we want is to have two images, detect key points in both of them, describe them, and then match them. So we can find the same object in different images. Okay? So the homography is going to filter the matches and keep only those that are interesting, that are important. And draw matches is a function that I wrote because the OpenCV.2.4.6 that is installed here don't have this function in Python. So well, here it will be the exercise if you want to do it, but I have the solution here. It's quite easy. It's just as I told you, extract the key points, describe them. This is the most important part here, and they have already implemented it. is to match those key points. How do you do that? You can do brute force, so just compare each key point with all the key points in the other images. But this is not very efficient, so what they use is Flan. Flan builds a hierarchical tree and starts comparing only in the same level. And they use ransack. So this will be the first step, feature extraction. So if we are talking about the kissing project, we will have a phase, for example, and we want to extract the features. But we have a lot of key points, so what we want is to use the bag-of-word technique. So we will have a lot of points in the face. We want to cluster them, so we have one eye, another eye, the mouth, so we can compare them. So how can we cluster them? Well, there are many, many algorithms. We can use connectivity-based clustering as word, the left example. K-means, that is the one that is implemented in OpenCV, in the bag-of-word technique, I mean. That is centroid-based, and density, that in this example is the best one. But this depends on the properties of your data set. So I have here another example of this, the same example if you want to play with it. You have 4 different clusters that you want to obtain. This is the desired result. And using K-means, this is only the important code. Cluster, mini-batch, K-means, that is a version that is faster than the normal K-means. And you use this code, and this is only to draw the results. You have the 4 clusters, and this is called the Voronoi diagram. So all the samples that lies in this region will be assigned to this centroid. And this seems very basic, but you can do really cool things. For example, we have this image of a shoe. We have all the data, and we want to cluster them. So we can start clustering the feature vectors. So we are clustering by similarity in the region of interest. So we will have the results. So these are similar, so they are clustered together. But then we want to split them, so we want to obtain each object in a different cluster. So we can apply, for example, optics, that is the density-based clustering. So you will have all the elements separated. This is very good because then you can create a graph joining. This will be the nodes. You can join them, and you will have a representation with a graph of the shoe. And the next step is to classify those nodes that we have. If we are talking about the kissing project, you will have 2 classes. They are kissing and they are not. So this is the main formula of the super vector machines. Well, this is the hyperplane. This is a constant that you set that tells you the penalty that you want to add to a sample that is going to be misclassified. We have, again, another demonstration. We have 2 sets. Let's assume that the blue is kissing and the green is not kissing. So the first thing we can do to separate them in this example is to draw a straight line. But we can define a lot of straight lines, so how can we decide what is the best? Well, the best one is called maximum separating hyperplane. And the key point is that it lies in between both, maximizing the distance between the 2 clusters. And these are called super vector machines that are used to define the line. But usually in the databases, we don't have these nice sets. We have a lot of noise, mixture, and everything. So you can use even more complex kernels. Kernel is a trick that we use that is just, we have this dimension, and we put all those things in a higher dimension. We find the hyperplane, and then when we go back to the original dimension, the thing that was an hyperplane can have different shapes, more complex shapes. And this is an example with polykernel, with polynomial kernel, radial basis function, and the linear we had before. Again, you can play with this data, and they have another kernel that you can use, and you can change the parameters as you want. Then another interesting property is that in the database, you usually have only a few information about a class and a lot of information about the other. For example, if you're training with images, you will have a lot of images with people not kissing and only a few of them that are kissing. So what we can do is to give more importance to those samples that are kissing. So then we can push the hyperplane. In this case, we are not giving importance to those points, to those green points. So what happens is that we are not classifying them properly. But if we give more importance to these points, we push forward the hyperplane, so we're classifying better. And of course, it's important to find or to estimate the best kernel. In this case, it's the radial basis function. Here I have the samples. Another technique, if you are working with clusters, is just instead of giving only weights, the same weights to all the class, give the weights depending on the distance between the point and the centroid. So you can see that it's very different. Here, the classification is overfitting. I will say it's overfitting, and in this case, it's more generalized because this point is very far from the centroid, so it has very low value. And well, we're ready for the part 3, but if you want to play with the code, it's now the moment, and you can ask us if you want. I guess you are playing, or no? What if you want, Jonathan?
Do you guys want some playing time, or should we move on to the next stage? It's up to you. All right. Right then, am I on?
Hello? Hi. Now we're going to sort of give you a little, well, it's part 3 now we're talking about, and in there is some code that you can sort of take home with you, play with, and we're just going to give you a sort of basic introduction to like the form of how you should sort of code some of this stuff, and then you can make it as complicated as you like as you take it home. I'm just going to briefly describe the sort of steps. The concepts have already been explained, so I won't go into too much detail. We start with our feature detection, so we take our image and we get a bunch of, features from it. Then we want to sort of reduce the complexity, so we do a bit of compression using PCA. So we get a bunch of, we'll get a mean and a set of eigenvectors, and then we're going to pick a subset of the eigenvectors. So we're kind of like choosing the most important, the sort of quintessent features of our data. After that, we'll move on to doing clustering. And then finally, with all of this information, we will generate a graphic model, which is to do with that sort of the PCA projection. And we're going to, from our clustering, we'll get centers, and that sort of describes our bag of words. And from that, we'll be able to, after that stage is done, we'll work to compute new features in terms of the pre-existing graphic model and the bag of words, such it's sort of described in a similar basis. And then we can move on to throwing these things at classifiers later on. And this is sort of how we do the computing features in terms of the bag of words. So for each image, we get all the features, and we're just going to stack them, so we get one big sort of matrix. Then we do the PCA project to get it in the same basis as our graphic model. Then we're going to calculate the distances from these objects to the clusters. And this isn't exactly what we want, because the distances are obviously going to be small when they're close and big when they're far away. And in fact, we want a sort of weighting, a smoothing function, so that when our sort of feature is close to our center, then it's big, and when it's far away, it's small. So we just invert that with a parameter we call the discriminator. It's something you can test and see, does it work well in this application? It's kind of trial and error at that point. And then because we've sort of messed about with this weighting, we need to sort of normalize our data. So we normalize the guy, so the error is 1. And then we do a mean of the entire stack. So we just get one histogram, which well represents that particular image in terms of our bag of words. And we use this thing to throw out our classifier. So if you go and have a look at your part 3 folder, 3 fingers, there we go. And I'm going to sort of talk you through the code a bit. Where is it? Is it the other side? There we go. All right, part 3. So, all right, there's a whole bunch of files in here. CIF features are just a whole bunch of basic functions, sort of doing the feature extraction we were doing before, loading images, etc. Not particularly exciting. So we're going to start on our bag of words. And it will open, hopefully. There we go. Everybody see it? Right then, we just start with some defining our class. So it's a bag of words. We do some initialization, so it's either going to take a detector or descriptor or a path where we've saved the previous model of this class. Then we do, using the detection and descriptor stuff, there's functions to save using pickle and load. So it's nice and easy. You can port this model about wherever you like. And
Can you make the font a little bit bigger?
yeah, how do I do that? There we go, be in here somewhere. Hope so. Do you know? View, what? Sorry. I don't know, sorry. I'm not very good with Macs. No.
That's a keypad plus, so yeah. And this one.
Sorry about this. There you go, font. Try that one. Be somewhere there. Bigger, please. All right, we'll just have to continue. Sorry about that. But either way, you can download the code and look at it, and I'll try to describe it in words anyway. So the important sort of function here is our train function, and this will take a whole bunch of paths from a sort of a training set, and defines a whole bunch of parameters, k, which is the number of clusters we're going to have in our, when we do our k-means, and the criteria. So this is sort of like the acceptance criteria, the amount of times you want to do it, because we're using random centers. It just places random centers in feature space, and then we'll calculate the distances and do that a bunch of times, and then the sort of the best correlated ones it will choose as its sort of optimum clusters. So yeah, we're just saving some parameters, get our detector and descriptor, then we're going to load in our first image from the path, so the first path, and then we're going to iterate over all of the rest of them and concatenate upon that array to get our sort of big fat stack. And there's just a little check there to make sure it doesn't add key points if they're none, because occasionally your key point detector won't find anything, so it will return you none, and you don't want to concatenate that to the stack because it'll mess up everything else later. Then the next stage is to do the square root on that. That's useful for PCA. It gives you a little bit of extra sort of performance there. Then you do a mean on the whole thing to get a single histogram, and then you throw that at your PCA compute to get your mean and your eigenvectors. Then you do that stage again, but inputting all of the stuff you had before. And this time, you're specifying the number of the best eigenvectors you want back out, and that was one of the parameters you gave it. And sort of a default one I used was 96, but you can play with it and optimize and sort of do some parameter bashing to see which one's best. And if you write nice portable code, then you can just sort of take them along with you. So after that, you just return out, you do your k-means, your last step, and then return out your mean, eigenvectors, and centers. And that forms, well, the mean and the eigenvectors form your sort of PCA graphic model, and the centers your bag of words. Right now, let's run this, wherever it is. So I'm just going to use IPython for convenience. Which one is it? That one. Got it. There we go. Thank you. All right, then at the end of the function, you have end of the file, you have a function called demo. If you run, it will go and compute you your very first bag of words. And if you sort of have a look, it's just getting paths with a module called datasets, and that's just got some useful functions for sort of looking through directories and pulling out JPEGs and stacking a big list of them. And it's also got some useful functions for doing creating reports after you've done the SVM and a whole bunch of stuff there. So that gets you out all your paths. And we're going to use the sort of the dataset/pos for our sort of training example. And we just specify detector and descriptor, we train our model on the paths, then we save it. And just to show you it being portable, I've deleted it, reloaded it from the file, and then just print out the answer at the end, which is, once it's done, it should spit that stuff out. All right, the next thing I want to show you, wherever it is, part 3, is actually doing the computing stuff in terms of the bag of words. And that's this file here. So going to do a little bit of inheritance, so we inherit our bag of words. Then we do our detect and compute project, which takes the key points using your detect and compute, projects it into the basis of your graphic model, and then just has a little check stage for if it got an invalid thing, it just creates a vector of the same size filled with zeros, and you add that instead of your failed guy. And then you'll actually compute the feature itself in terms of the bag of words. And then what we're doing here is getting our projection. Then we're doing the distance using a metric. And this metric is specifiable. We picked Euclidean for basic ones, but you can do city block, which will just go along like squarewise vertices. If you look at the documentation, there's a huge range of functions to play with, so you can sort of have a little mess about with that. And then we invert those distances with our discriminator as described, so you can pick a different power, see that how that kind of works. And then, because if we had any zeros in the bottom, they would have blown up to infinity, so we set them back to 1. Then we just renormalize and output the last stuff, and then we just save it for this demo. So hopefully the other demo is finished running by now. Hopefully. Yeah, and that's sort of the last one. So we're going to run this new file, feature computer, do a demo. And this one is just proving it does what it says it does. So it's going to load up the graphic model which we generated in the last demo. Then it's going to just compute the values compute the histogram for a particular file there. Now we're going to move on to more interesting stuff, which is the sort of the final big stage. And that's the SVM trainer tester, which I'll just describe. So, okay, the first function I'm going to talk about takes your model, which we've generated, so your vision model or your bag of words guy, then takes some parameters and an ID. Then it generates, using our dataset generator, the train set paths, the labels for them is +1 if it's a KISS, -1 if it's not. Then we generate a test set and test set labels from these given paths, so it's going to go through the pos, neg, pos2, neg2, and the last things are just specifying how much you want for each. Then we will stack all of those features for the training data, so we just compute all of those guys and have a nice V stack at the end of it. And then we're going to initialize our CV2 SVM. And then this stuff's interesting. We were talking about the parameters used for sort of optimizing your SVM. Fortunately, OpenCV has a sort of a really nice tool where you just define grids of your parameters and throw it at it, and then it will go through cyclically through all of them and work out the best ones. And sort of your gamma is to do with it's to do with the RBF. It's sort of the size and the scope of it, and your C parameters, which are to do with penalizing outliers in the system. And then you give it some training data with the labels, you give it a whole bunch of parameters, and then you say go. And it runs for a little while, and then it will generate your SVM, which is contained in that little guy there. Then next thing, we want to test it, so we do some get our test data, and concatenate the stack for that guy. Then we give it, get it to predict all its labels, and then this is a bit messy, but it just computes the success rate given sort of comparing the labels given what the SVM threw out. Then we want to save it. Then we want to generate a nice little report. Then we're going to save our model, and then the return types, it returns the current K value, so the number of clusters for your particular model, the maximum components, which is the number of eigenvalues, and finally the success rate. And the reason why we want to do that is because we're going to want to throw these guys at our, we've got a param bash function, which will iterate over a whole bunch of Ks, a whole bunch of Es, and then generate models using those parameters, and then it will do that for all of them, and then it will go and draw a grid, so we can actually see which parameters we're doing best. And so if you use lots of data, you may want to iterate over more than just 2 parameters. I mean, when we were doing our project, we had a whole sweep of them, drawing nice little 3D graphs, etc. And then the final thing, we just want to draw this sort of grid out, and we're just going to set sort of the y-axis. Well, I'm not going to explain it. It draws a graph, and it will plot them, and then the lighter the color of that particular node, the better the performance of that sort of parameter set. Now, running this guy here is going to take a little while, because it's quite, if you're using Wackery, it will certainly take a little while. SVM, this guy, and then run param bash. Now this will iterate all of it, generating our new models, evaluating their performance, and while it's doing that, it's going to be generating reports and putting them in the directory with your model and everything you sort of get with you. So here's an example of one of the output files. So that it's a 0th model. It saves the model itself, and you have a nice little report. And we can have a little look, and this one did 70%. Here's the positives and negatives. And then after this thing has run for a long while, you'll get one of these images out. It will spit it out as a graph. And here you can see the sort of like the variation. As I said, the lighter colors are the better performance. So there'll be sort of 100% there. That might be worse. And as I said, you may want to iterate over a whole bunch of them and check out different parameters, mess with the discriminator, and that's sort of left for sort of a bit of homework, as you like, to go and mess about with this stuff. And you can swap out the feature vectors, use different ones. Maybe start using some of the Harris ones that Bertrand was sort of doing. And then, not again. And so, yeah, that's essentially it. As I said, this guy will take a little while to run, so I'll sort of get back to Bertrand for a minute.
I don't know if it's working. Yes. Well, that was all for this tutorial in terms of content. But I think there's a lot to be done to play with the code that we have submitted to you. And as I said, it's a tutorial, and we expect it to be interactive. So we thought at either doing the exercise by making a break in the presentation, or either doing a session where we stay with you and we have a look and we answer your question, and that's what we will be doing now. I thank you a lot for your time and for your attention. If you have questions, so do not hesitate to ask us. I've put the slides, if you want to access the slides, on our Twitter. So it's @widio. You can find the slides there if you need to. Sorry, it's not what I wanted to do. It's just that's that one. I think it's been. Well, it's @widio for the slides. And you can, and otherwise, yeah, we're here to answer your questions for the next 20 minutes. Thank you.